In this class, we will discuss about the chapter haloalkanes and haloarenes. And first of all, we will go through the important topics of this chapter that we should prepare for your NEET exams. And then we will go to the topic-wise questions as well. Okay. So first, we are moving to the important topics from the chapter. So first, let me share my screen. So first, let us go through the important topics from the chapter. So first of all, we have to know what are haloalkanes. Haloalkanes are containing halogen atom in the hydrocarbon, right? So from the hydrocarbon, that is from alkanes, alkenes or alkynes, whatever it is, we can replace the hydrogen atom with halogen atom. Those kind of compounds are called haloalkanes, and they are usually represented by Rx. Here R is the alkyl group and X is the halogen. So they are called haloalkanes. Now coming to the haloarenes, arenes means they are aromatic compounds. Okay, haloarenes means we are replacing the hydrogen from aromatic compound by halogen. Then you will get haloarenes. So both haloalkanes and haloarenes, they are derivatives of hydrocarbons. Means they are produced by replacing hydrogen atoms from the hydrocarbon. The hydrogen atom will be replaced by the halogen atom. Okay, so they are of three types: primary, secondary, and tertiary. In primary, only one means the halogen atom connected carbon will connected to one alkyl group. For example, I'm taking methane. I'm taking ethane. Okay, so in ethane, I'm replacing one hydrogen with one chlorine. So this is chloroethane. Now see, the halogen connected carbon is this, right? This is connected to only one carbon. So this is a primary haloalkane. Now we have a secondary haloalkane. It means one more hydrogen will be replaced by the alkyl group. So it will be CH3H CH3Cl. So here we can see two alkyl groups, right? Means the halogen containing carbon is this one. This is connected to two carbon atoms, so they are secondary. So here the black one represents the alkyl group and the white one represents the hydrogen. So coming to the tertiary, here this is the halogen. So halogen containing carbon is connected to three alkyl groups, so three carbon atoms. They are called tertiary haloalkanes. So this is the classification. Now, for example, we can say one chloropropane, two chloropropane. One chloropropane is, this is an example for primary. Okay. And this is an example for secondary. Then this is a dihalide, means more than one chlorine atoms will be replaced. And there are different kind of haloalkanes. Okay. Now see, here we can see one chlorobutane because the chlorine is present in the first carbon, two chlorobutane. So this is the classification. Now coming to the physical properties, when there is an increase in the size, molecular size of haloalkanes, usually their boiling point will increases, because when the size is increasing, the van der Waals interaction will increases, right? Because the boiling point is completely depending on the intermolecular forces, and in halogenoalkane we can see the type of intermolecular forces is van der Waals forces. So when this van der Waals force increases, it becomes hard to break the bond between the halogenoalkane molecules. It means their boiling point will increases. So this is about the boiling point. So when the chain length is increasing, their boiling point will increases. Now coming to the solubility, usually the haloalkanes will be soluble in organic solvent but insoluble in water. Okay, soluble in organic solvent but insoluble in water. That also you have to remember. Now coming to the important reactions of this haloalkanes. The first one is the nucleophilic substitution reaction. Substitution reaction means one species will be substituted by or replaced by some other species, right? So what is nucleophilic substitution? One nucleophile will be substituted by some other nucleophile. That is called nucleophilic substitution reaction. So if you consider the halogenoalkane, the halogen, that is the whatever the halogen, either chlorine, bromine, iodine, the halogen can be substituted by the corresponding another nucleophile. Another nucleophile can replace the halogen. Okay, and those kind of reactions can be called as nucleophilic substitution reaction. That is, the halogen nucleophile is substituted by some other nucleophile. Now, why they are showing the nucleophilic substitution? That is the question, right? So here I have a halogenoalkane. So whatever it is, it may be some R group, it may be hydrogen, it may be some other R dash, whatever, primary, secondary, tertiary. Here, this bond between the carbon and halogen, right? The bond between this carbon and halogen means the bond between the carbon and chlorine. This is a polar bond. Usually the carbon hydrogen bond is a non-polar bond, while the polarity is completely based on the electronegativity, right? So coming to the hydrogen, both carbon and hydrogen atoms are having similar electronegativity values. So the bond is non-polar. And C, if you take the Cr, means R is the alkyl group. So there will be a C-C bond. C-C bond is also non-polar because there is no any difference in electronegativity. The same time, if you consider C-Cl bond, this chlorine is partially negative, carbon is partially positive. Why? Chlorine is more electronegative than carbon. So here CCl bond is polar in nature. Okay, as a result, this bond is highly reactive. That's why they are undergoing nucleophilic substitution. Means this chlorine can be substituted by some other nucleophile. Okay, so that's what here shown. That is the del plus. This is the carbon. Del minus is the halogen. Either it is chlorine, bromine, whatever it is. Okay, so this is the nucleophilic substitution. Now, the nucleophiles means they are of different kind of nucleophiles are usually electron-rich species, right? They can donate the electron pairs, right? So OH minus, it is a nucleophile. Cn minus is a nucleophile because in OH minus we can see there is a negative charge, and here oxygen is containing lone pair of electron as well. So that lone pair of electron is able to donate. So bases nucleophiles are usually having basic character, means they can donate the electron pair. They are electron pair donors. Okay. If you come to Cn minus also, here carbon is the donor atom. Okay. If you come to NH3, this is not negatively charged, but still ammonia is a nucleophile. Why? Because in ammonia, nitrogen is containing lone pair of electrons, right? That lone pair of electron is able to donate to some other species. So they are also nucleophilic. Now coming to water, in water oxygen is having two lone pair of electrons, right? So these lone pairs of electrons can be donated to some other species. So water is also acting as a nucleophile. So this is the nature of nucleophile, means this is how they are acting as a nucleophile. Okay. So in the nucleophilic substitution reaction, as I explained now, this green color is representing the halogen, whatever it is, and this is carbon. So this halogen or this chlorine will be substituted by the nucleophiles such as Cn minus, ammonia. Okay, because the chlorine is leaving with the electrons. They are taking the electrons. That's why the carbon is getting the positive charge. So the carbon become the electrophile, right? Electrophile means electron deficient species. They needs electrons. So that electrons will be given by the nucleophile. Okay, this is what happening in case of nucleophilic substitution reaction. So this is how we can represent the nucleophilic substitution. Here we can see this is the CCl bond. This black one represents carbon. This is the halogen. So this is the CCl bond is polar. So during the substitution, the nucleophile, whatever it is, whether it is water, ammonia, whatever it is, they will come and they will attack the positively charged carbon. Why? The CCl bond is polar, right? So this nucleophile having the negative charge will attack the carbon, then the Cl bond will remove. This chlorine will leave. So chlorine is the leaving group and nucleophile is forming a new bond with this carbon. So this is the nucleophilic substitution. This is the leaving group, chloride ion. Okay, this is what happens in nucleophilic substitution reaction. So here the reasons are the bond is polar, and here the curly arrows are very important. We can see the questions from this topic. Okay. So this is the, but see, so this nucleophilic substitution reactions are of two types actually. They have two kind of mechanisms, SN1 mechanism and SN2 mechanism. So the one that I have explained here is a type of SN2 mechanism. SN2 mechanism means it is a single step process. That is, the nucleophile will attack the carbon and the leaving group is leaving. Both takes place in a single step. Nucleophiles at a nucleophile attack and the leaving of the chlorine atom. Both are taking place in a single step. Okay, so that is what happening in case of SN2. So the single step process is called SN2 mechanism. Okay, now we have one more mechanism, that is, see, here we can see the animation. See, this is the leaving, this is the attacking agent. So when they are attacking through backside, the leaving group is removing. Right? See, this is the mechanism. Okay. So here the thing is, the attack of the nucleophile is possible from the backside only. Why? Through this side, the attack is not possible. The nucleophile cannot come through this side because here is the leaving group. So due to the steric repulsion, the same side in which the chlorine is attached, the attack of nucleophile is not possible. Okay, that is the thing regarding SN2 mechanism. So there will be always a backside attack in SN2. Okay, now which is the good leaving group? So halogenoalkane means the halogen may be chlorine, bromine, fluorine, iodine, whatever it is. Okay, so in case of this thing here, when the halogen, different halogens are coming, how they are affecting the rate of this substitution reaction. Usually the size of the halogen atom increases down the group, right? So fluorine is less than chlorine, which is less than bromine, and iodine is the biggest one. So biggest ions are forming weaker bond with the carbon atom, right? So among these four, iodine is producing the weaker bond with carbon in halogenoalkane. So that weaker bonds are easy to break. It means the iodine can be removed easier than bromine or chlorine or fluorine. So when the size of the halogen increases, means it become a stronger leaving group. The substitution reaction become more easier. That's why the iodides are, means haloiodides are undergoing this substitution more faster than other type of haloalkanes. And see the bond energy. See, this is having the lowest value, which one? Carbon iodine bond. That's why they are good leaving group. Okay. See, here we can see example as well. Bromoethane react with water. They are producing ethanol, H plus ions and Br minus ions. And this is another one, Ag plus plus X minus is producing Ag. So these are experimental evidences. Okay. Now, usually the nucleophilic substitution reactions takes place in potassium, that is aqueous potassium hydroxide. This is important because in some other reactions that we will discuss later in elimination, okay, that there also we have the same like base is there, but the reaction medium is different. Here it is aqueous sodium hydroxide, means we are dissolving sodium hydroxide in water and we are using it. Right. But there are alcoholic sodium hydroxide medium that will come in the elimination reaction. So this is important. So based on the C, everything will be same. The reagent will be same. Sodium hydroxide will be same. But the product or the reaction, whether it is either if it is elimination or it is substitution, that can be predicted on the basis of aqueous and alcoholic nature of the compound. Okay, that is also important. See, this is the animated mechanism for the nucleophilic substitution reaction. See, here this is the carbon containing positive charge. It will be attacked by the nucleophile and the leaving group is removing, and they are producing the substituted product of the reaction. And this is the leaving group. Okay. Now, if you want to replace the halogen with Cn minus ion, we can use potassium cyanide. This is another kind of reaction. So here we can take aqueous or alcoholic potassium. If you want to replace the halogen with OH minus ion, we have to take aqueous. But here if you want to replace the bromine with Cn minus ion, we can take either aqueous or alcoholic potassium cyanide. Okay, this is the important difference. Okay, see. Potassium cyanide, the same mechanism will be same in all cases, but see, in Cn minus carbon and nitrogens are connected by this triple bond. That is the difference. Okay. This is the mechanism. Now, if you want to replace the halogen with ammonia, that is also nucleophilic substitution, because ammonia is containing lone pair of electrons on nitrogen. This will act as a nucleophile. So here also this is the mechanism. Mechanism is anyway it is same. Only the attacking reagent is changing their shape or anything, right? So here we can use either aqueous or alcoholic ammonia in excess. This is important here. So in some reactions the reagent is important. In some reactions the medium of the reagent is important. In some reaction quantity, whether it is we should use it in smaller amount, excess amount, that is also important. Okay. So these are the things that you have to remember. Now, why we are using the excess ammonia? That is also very important. See, in this reaction, we can see in the first step we are not getting, see, when this haloalkane is reacting with ammonia, we are getting the product which is an amine, right? So I will write the mechanism here, CH3, CH2, Okay, this is the reactant, bromoethane. So the leaving group is bromine. Now when ammonia, NH3 is coming, using the lone pair, the NH3 will attack the carbon, then the bromine will leave with the electrons, right? So the product you are getting will be CH3. These hydrogens are not removing, only the bromine will be replaced by NH2. So here we can see NH3. So here we can see here NH3 is there. Right, but now the nitrogen is having a positive charge. So this is not the final product of the reaction. We need an amine, but here it is NH3, right? So what happened, one more NH3 will be reacting here. Using the lone pair of electron, one more NH3 will take the hydrogen in form of H plus ion. The hydrogen is removing in form of H plus ion because NH3 is a base, it is ammonia. So they are acting as a base means they are proton acceptors. So this NH3 can abstract the H plus ion from this species produced in the reaction. So H plus means the hydrogen is not taking these electrons. So these electrons will move on the nitrogen atom. So what is the product you are getting? It will be CH3, CH2, then see this hydrogen is removed and this electron pairs are moving on nitrogen means nitrogen is getting the lone pairs back. So this product is obtained. So this is how we are getting this amines, means after the substitution of this halogen with ammonia, the final product is an amine. But here comparing to the other reactions, we have an extra step here. That is this second step. That is the second ammonia molecule is attacking the product obtained in the first step. That is they are abstracting the H plus ion, right? So this ammonia it will come if you are using excess ammonia. Otherwise it is not possible. So here they are producing NH3 is taking H plus and they will produce NH4 plus ammonium ion. Okay. This ammonium ion will react with the leaving group bromine and they will produce ammonium bromide. So anyway, in order to produce this amine, the next ammonia should come. Then only they can take the hydrogen as H plus ion. So this step is compulsory here. Okay, so that's why they are always telling we have to take excess ammonia. The excess ammonia can only convert the product into amine. Okay. Now here you are getting a primary amine, right? Primary amine means the nitrogen of the amino group is connected to only one alkyl group and two hydrogens. So what is a secondary amine? Secondary amine means the nitrogen will contains two alkyl group and hydrogen. So in this reaction, the reaction that I have written here you are getting a primary amine, right? If you want to produce a secondary amine, this primary amine should react again. Instead of ammonia, you have to take a primary amine. That primary amine will react with another molecule of alkyl halide, right? Then you will get a secondary amine. So if you want to produce a secondary amine, if you want to produce a tertiary amine, the secondary amine produced in this step should react with another molecule of alkyl halide. Okay, instead of ammonia, you are taking primary, secondary to produce the next one. Okay, this is how we are preparing, this is how we are doing the nucleophilic substitution reactions of halogenoalkane. Okay, so these are the rules and mechanism of the reactions. Okay, you can write it down, note them down. Okay, hope this is done. Now we are moving to the elimination reaction. So in order to take place the substitution we were taking, means if you want to replace the halogen with a nucleophile hydroxide ion, you are taking the aqueous potassium hydroxide or aqueous sodium hydroxide, right? Now here the elimination reaction. So elimination means you are taking alcoholic sodium or potassium hydroxide, alcoholic. So what will happen? Instead of substitution, elimination. So here the alcoholic, that is important. Alcoholic sodium hydroxide will produce only the eliminated product, not the substituted product. So what is an elimination reaction? Elimination reaction means the halogenoalkanes when react with alcoholic sodium or potassium hydroxide, they can produce an unsaturated hydrocarbon or alkene. That is simply elimination reaction. Okay, so if you take this reactant, that is the halogenoalkane, here we have to take the alcoholic potassium hydroxide, I told you, right? So here also we have the OH minus ion which is produced from the potassium or sodium hydroxide. This OH minus ions will abstract H plus ions. Why OH minus ion? See, I will write the proper one. That is, here we have an alcohol. Here we have an halogenoalkane. I will write chloropropane. Chloropropane. So this chloropropane is reacting with alcoholic sodium hydroxide. From alcoholic sodium hydroxide, this sodium hydroxide will always release what? Na plus ions and OH minus ions, right? So this OH minus ions can abstract the H plus ions, right? Because OH minus ions are bases, they are proton acceptors. So they will take the H plus ion, so not the bond. So when they take the H plus ion, the bonded electrons will shift to these two sides. So this chlorine will leave. So the chlorine attached carbon is called alpha carbon and the adjacent carbon is called beta carbon. So this elimination will take place between the alpha and beta carbons only. So you cannot abstract the hydrogen from this carbon. Why? Because this is not the beta carbon. Beta carbon means the halogen connected carbon is there, right? The adjacent carbon is called beta carbon. So here the beta carbon is only this one. Which one? This second one is the beta carbon. This is not the beta carbon. Okay, because this is the alpha carbon. So the beta carbon, the hydrogen from the beta carbon will be abstracted by the OH minus ions in form of H plus ion. So the bonded electrons will move between the carbon atoms and the halogen will leave and they will produce the corresponding alkene as the product. Okay, so this is how the halogenoalkanes are converting into saturated hydrocarbon. Okay, this is the sorry, how the halogen alkanes are converting into unsaturated hydrocarbon. So this is elimination. As I told you before, this takes place in presence of alcoholic potassium hydroxide. Okay. So these are the important, see here we can see an animated mechanism. See, so this is the OH minus ion, okay. See, they are abstracting the hydrogen. This is a hydrogen, electrons are moving, and this is the alpha carbon, this is the beta carbon. The halogens, the hydrogens will be abstracted by the OH minus ions in form of H plus ion. So this will be moving towards they will be moving between alpha and beta carbon. Electrons will move, so they will produce the corresponding unsaturated alkene. Okay, so this is the reaction. Overall reaction takes place here. Okay. Now let us go to the past paper questions from halogenalkanes and haloarenes. Okay. Now let us discuss the questions from this topic, haloalkanes and haloarenes. So coming to the first question, here it is given that a reaction, that is iodopropane, react with sodium cyanide and they are converting into a product A. And this A is undergoing partial hydrolysis to produce B, and B on reaction with bromine, they are producing C. So we have to find out the final product, that is the major product C in the reaction. First, let us start from the reagent, that is iodopropane, right? So I will write the whole equation here. CH3, CH2, CH2I. This is iodopropane. So they are reacting with sodium cyanide, NaCN. So first thing here, this iodine will be replaced by Cn. This is what I explained before, the substitution reaction, nucleophilic substitution reaction. So here the Cn minus ions will be replacing the iodine because iodine is the leaving group, which is a nucleophile, I minus ion. Cn minus is another nucleophile. So when the Cn minus is attacking this carbon, this iodine will be removed and they will produce CH3, CH2, CH2, Cn. So this is called propane nitrile, right? Because they are containing 4 carbon atoms. So they are propane nitrile. So this is A, which is producing here is propane nitrile. Sorry, not propane, butane nitrile, because 4 carbon atoms, right? 1, 2, 3, 4, 4 carbon atoms. So they are butane nitrile. Okay, now what is the second step? This butane nitrile is undergoing hydrolysis, partial hydrolysis. So when they are undergoing partial hydrolysis, this nitrile group, that is, this is butane nitrile now, this is converting into corresponding amide. So the product will be, I will write the remaining here, CH2, the CN group will convert into CONH2 group. This is the difference. The CN group get converted to CONH2 group. So this is B in the reaction. That is the amide. Amide. Okay. Now see what is the next reaction. This B is again reacting with sodium hydroxide in presence of bromine. So when they react with sodium hydroxide in presence of bromine, they will convert into corresponding amines, right? So it will be CH3, CH2, CH2, NH2. Okay. So you are getting propylamine. This is the reaction. So here you are getting butane nitrile, they got converted to amide, then the final product is propylamine. So correct answer will be option C. Now the second question. Here also we have a series of, we have a reaction. We have to find out the final product X in the reaction. But here we have a series of reagents, right? So we have to use the reagents properly to find the product X. So we can start from the reactant first. So the reactant is an aromatic compound, right? So here we can see C2H5 here, aromatic ring, then the nitro group is there. So here the first reactant is chlorine in presence of FeCl3. So this reactant is used for electrophilic substitution, right? Electrophilic substitution. Because in presence of FeCl3, because which is a Lewis acid, this chlorine can act as an electrophile. So this electrophile can remove one hydrogen from benzene and they will produce the substituted product, means the hydrogen will be substituted by chlorine, but other substituents will remain unaffected. Okay, so this is the first one. So this is the first product of the reaction. But the reactants are not finished. We have two more reactants. So when this thing reacting with tin and HCl. Tin and HCl means they are reducing agents, right? So here we have nitro group which will undergo reduction easily. So in presence of tin and HCl, other groups and the ring will be remains unaffected, but this NO2 group will undergo reduction. When they are undergoing reduction, they will produce NH2. Means the NO2 group gets converted to NH2. This is happening in with the second reagent. Okay. Okay. Now, next one more reactant is remaining, that is NaNO2 and HCl, because we have done with tin and HCl. So next one is NaNO2 and HCl. This NaNO2 and HCl at a temperature of 2, see we have one more potassium iodide is also there. Okay. So NaNO2 and HCl, sodium nitrite and HCl, this will convert into the diazonium salt, because sodium nitrite and hydrochloric acid, these are diazotization. This reaction is called diazotization reaction. They are diazotizing agents. So NH2 group will undergo diazotization and they will convert into the corresponding diazonium salt, that is N2Cl, C2H5 is there, chlorine is there. Okay. So this is the diazonium compound of the given reactant. Now we have, so the role of the third one is also done. Now we have one more, that is potassium iodide. Now when this diazonium chloride react with the potassium iodide, the product will be, the diazonium group will be substituted by iodine, means this entire group will be substituted by iodine and the product is aromatic ring will be there, but instead of the diazonium group it will be iodine and chlorine is still there, C2H5 is also there. So this is the product, final product of the reaction. Okay, so in the first step, see here we have a series of reactants. So the reactant, which is a nitro compound, aromatic compound, first step they are reacting with chlorine and iron ferric chloride. So they will undergo electrophilic substitution reaction, because FeCl3, in presence of FeCl3, chlorine will behave as an electrophile. So they will replace hydrogen by chlorine and produce the substituted product. This substituted product will again react with tin and HCl. This is a reducing agent. So in presence of this reducing agent, they will convert into the corresponding reduced species. So who will undergo reduction? The NO2 group, nitro group will be undergoing reduction and they gets converted to NH2 group. Now this compound is again reacting with NaNO2 and HCl. So from this reactant itself it is clear this is an example for diazotization, right? So the reaction takes place here is diazotization, that is the NH2 group will be converting into diazonium salt. So when they react with the last reagent potassium iodide, the diazonium chloride, means the diazonium group will be replaced by the iodine and they will produce the final product. So this is the overall reaction here. So from these options we can see the first one is not the correct one, second one is also not correct, and the correct answer will be the third one. Now let us discuss the next question. Here also we have a reaction series and we have to find out the final product C in the reaction. So this is also similar to that of the first question, right? Okay. So we are starting from the reactant. The reactant is bromopropane. Means bromine atom is present in a 3-carbon chain. So this is bromopropane. So the first reactant is alcoholic potassium hydroxide. So this is what I explained before. If the reactant is aqueous potassium or sodium hydroxide, the reaction will be substitution. If it is alcoholic sodium or potassium hydroxide, the reaction will be elimination reaction. So here this bromopropane will undergo elimination reaction, not substitution reaction. So I will first I will write down the product in the first step, CH3CH2 CH2Br. They are reacting with alcoholic potassium hydroxide followed by heating, right? So here, what is the elimination? Here the alpha carbon, this is the alpha carbon, this is the beta carbon. Between alpha and beta carbon, there will be a double bond formation, right? This is the elimination reaction. So it will be CH3, CH2 means one hydrogen will be abstracted by from the beta carbon, one hydrogen will be abstracted by the OH minus ions and this bromine will also leave. So this is an example for dehydrohalogenation. Elimination is, here the elimination is also called dehydrohalogenation. Means hydrogen is removing and halogen is also removing. So this is A, that is propene. Propene. Okay, so A is propene. Now what is the reaction? This propene react with HBr, hydrogen bromide. So this is the opposite reaction of elimination. When you are adding a hydrogen halide into an alkene, the reaction will be the addition reaction. That is opposite to that of the elimination reaction. Okay, addition reaction. So when this molecule is undergoing addition reaction, here hydrogen bromide, right? So hydrogen will add to, so this hydrogen halide is adding between the double bonded carbon atoms. So the halogen will move to the carbon which contains less hydrogen. That is the Markovnikov's rule, right? So here the product will be CH3CH, the bromine will move here and the hydrogen will move here. So it becomes CH2 becomes CH3 and this carbon becomes CHBr. The bromine gets added there. So this is 2-bromopropane. 2-bromopropane. This product is the product B in the reaction. B. B is 2-bromopropane. Now the reaction is not yet means they are not yet finalized. We have one more step, that is they are reacting with aqueous potassium hydroxide. See, here we are using potassium hydroxide, but it is in aqueous form. Aqueous form means the reaction will be what? Substitution reaction, right? See, in elimination and substitution, we are using same reagent, potassium or sodium hydroxide, but the reaction medium is different. In substitution, we are using aqueous. In elimination, we are using alcoholic. So here, in presence of aqueous KOH, they will undergo substitution. That is, the bromine will be substituted by the OH minus ion, right? So they will produce CH3, CHBr, CH3. That is, sorry, CH3. This bromine will be substituted by hydroxyl group. So this is propan 2-ol. This is the product C in the reaction. Propan 2-ol will be produced. So from these options, option B is correct. Okay. So when the reaction medium is changing, the entire reaction is also changing. That is the important thing regarding this. Now, next question. Here a compound is given. We have to find out the category in which this compound is belongs to. So from this structure it is clear this is containing a halogen. So this is a halogenoalkane, right? So now we have to see which category of halide this is belongs to. So it is confirmed it is a halogenoalkane or alkyl halide. So first we will write the first observation. This is an alkyl halide. Okay. Now we have to know in alkyl halides itself we have different kind of alkyl halides, right? So we have to consider, we have to find out which alkyl halide is the given compound. So here we can see that this halogen is connected to one carbon, right? And this halogen connected carbon is the sp3 hybridized carbon. Okay. And this sp3 hybridized carbon is again connected to a carbon-carbon double bond. So halogen is connected to sp3 hybridized carbon, which is again connected to a carbon-carbon double bond. So this is belongs to a type of alkyl halide, and it is called allylic halide. Allylic halide. So this given molecule is an example for allylic halide. So correct answer is D. Now the next question. Here we have two statements, right? So we have to find out the incorrect, here we have four statements. We have to find out the incorrect statement from these options. All these statements are regarding with chirality. So we have to choose the incorrect one. First of all, we have to know what is a chiral carbon. So this chiral carbon, the importance of chiral carbon is in optical isomerism, right? So the compounds, organic compounds which containing the chiral carbon will be optically active. Optically active means they can rotate the plane of plane polarized light, right? So if they are rotating into left direction, the compounds are levorotatory. If they are rotating into right direction, the compounds are called dextrorotatory. So based on their nature, we can classify them, right? So this optical isomeric property means the ability to rotate the plane of plane polarized light, right? So this is happening in a compound. This will be possible in a compound if the compound is containing a chiral carbon. So chiral carbon means the carbon which is connected to four different groups. Okay, four different groups means it is not like see, here we have C2. This carbon is connected to halogen, hydrogen, CS3, C2H5. Don't think like this carbon, this is also carbon, this is also carbon. We are not checking the atom only. If it is a group, we will check the entire group. So this is ethyl group, this is methyl group. So they are different. So don't think like the atom which is connected to the carbon. It is not like that. If it is a single atom, it is fine. If it is a group like alkyl group, we have to check the entire alkyl group. So this is CH3, this is C2H5. Both are different. And now here we have hydrogen, here we have halogen. So here all the four groups connected to this carbon are different, right? So this red carbon is the one that I am circling using the red pen. This carbon is the chiral carbon. Chiral carbon. Okay. This is what is happening in case of chiral carbon. This is how we are identifying chiral carbon in a compound. Okay, so let us see the options. So chirality is clear. Hope this topic is clear. So let's see the options. The product obtained by SN2 reaction of haloalkane having chirality at the reactive site shows inversion of configuration. That is correct, right? Because SN2 mechanism means this is what I explained in the topic, right? Right. The SN2 means it is a one-step process. Means the halogen containing carbon will be attacked by the nucleophile. At the same time, the halogen which is connected to the carbon will leave. Okay, so this is what I told you in that animation I have explained. When these OH minus, when the attacking nucleophile is coming, they cannot come through the same side of the leaving group because there will be some repulsion. So this hydroxide ion always can come through the opposite side of the leaving group. So you are always getting the product with inversion of configuration. You are always getting the inverted product because in the reactant you have this halogen in the right side, right? But in the product you will get the substituted product in the left side. This is the inverted product. So the option A is the correct statement. They are asking to find out the incorrect one. So option A is not the correct answer, but it is a correct statement. Now coming to option B, enantiomers are superimposable mirror images on each other. This is an incorrect statement because when the compound which containing chiral carbons are rotating the plane of plane polarized light, because these compounds will be optically active, right? So these compounds are optically active. So this optically active compound which is containing the chiral carbon can rotate the plane. Okay, rotate the plane of plane polarized light. And now, now we are getting levorotatory and extrarotatory. Okay, so that is possible if, see, the levorotatory and extrarotatory, these two compounds will be always the mirror images with each other. Means, suppose I have 100 number of molecules. Now I have some of the molecules are rotating the light into left direction, some of them are in right direction. So that molecules will be non-superimposable mirror images, means an optically active compound should always produce a non-superimposable mirror image. So if you take the mirror image of this given compound, they will be non-superimposable with this original one. So they are called enantiomers. Enantiomers are non-superimposable mirror images, not superimposable. So this is an incorrect statement. So this is the correct answer. Okay. Now coming to option C, if you check other options as well, coming to option C, racemic mixture shows zero optical rotation. That is correct because racemic mixture means it is a 50-50 mixture. Means suppose I have 100 molecules of a particular optically active compound, then the 50 number of the molecules are rotating the light in left direction, 50 is in the right direction. So what is the overall optical activity of the whole compound? That will be 0 because 50 is rotating left, 50 is rotating right. It means the overall activity is 0. So racemic mixture is the 50-50 mixture which has a 0 optical activity. Okay. So option C is the correct statement and incorrect option. Coming to the option D, SN1 yield 1:1 mixture of both enantiomers. SN1, SN2 I explained. SN2 means the attacking reagent is coming through the back side. But in SN1, it is a two-step process, right? In the first step, the halogen will remove the halogen and they will produce the carbocation. The second step means the carbocation will be attacked by the incoming nucleophile. But in case of that reaction, this is the carbocation, there is a possibility because in the first step, the leaving group already left. Okay, so the next incoming group can come either through the back side or through the front side. But in this SN2, we have only one possibility. They cannot come through the front side. They can only come through the back side. So here we have two, either through back side or through front side. If they are coming through the back side, you will get inversion. Okay. If they are coming through the front side, you will get the configuration, that is retention of configuration. So there is a chance of 50-50 chance. So we can say in SN1 reaction, we are getting 50% of inversion, 50% of retention. So they will be the enantiomers, that inverted and retention products will be non-superimposable mirror images, means they will be enantiomers. Okay, so option D is also correct statement and incorrect option. Hope you have written everything. Now coming to the next question. Here, the question is four series of reagents are given. We have to choose the correct sequence of reaction which is suitable for synthesizing chlorobenzene. Okay. So we have to produce chlorobenzene and which reagent we will use. So using phenol, we cannot produce the chlorobenzene using these reagents. So option A is not the correct one. And using benzene and HCl only also we cannot produce, because we have to do the electrophilic substitution. The reaction should be electrophilic substitution. Then only we can produce the corresponding chlorinated product, means chlorobenzene, because chlorine should act as the electrophile. So, okay, in order to, so usually chlorine, Cl2 is a neutral molecule, not an electrophile. In order to act as an electrophile, the chlorine should take in presence of a Lewis acid such as FeCl3 anhydrous iron chloride. Okay, so here we can write the reaction, that is benzene react with chlorine in presence of FeCl3, anhydrous FeCl3. What will happen, you know, here the hydrogen atom from the benzene will be replaced by chlorine. This is the reaction. If you want to know the mechanism as well, I can show you. This is the benzene molecule. So Cl plus is the electrophile which is attacked by the double bond, and they will produce this system, right? Chlorine and hydrogen. Now, in order to complete the resonance, the bonded electrons will come here. This hydrogen will be removed. So, they will produce chlorobenzene. This is the reaction. So, we need benzene, chlorine and anhydrous FeCl3. Then only we will get chlorobenzene from benzene. So, C is also not the correct one. Okay, and D is the correct answer. Benzene, chlorine, anhydrous FeCl3. So D is correct. Now in the next reaction, we have the reactant, that is, it is a nitrile, aromatic nitrile. We have to find out the correct product when we use these reactants. That is the question. So first we can take the reactant. It is an aromatic nitrile. Okay. When we are using, the first reactant is lithium aluminum hydride. So the reaction will be reduction, right? Because lithium aluminum hydride is a reducing agent. So during reduction, the CN group will be converting into CH2 NH2 group, because addition of hydrogen will take place. So they will convert into CH2 NH2, right? Now, second reactant is NaNO to HCl. That is the diazotization reaction, or diazonium chloride will be produced. Okay. Here the NH2 group will be converting into the diazonium group. So it will be CH2 N2Cl. Okay. Now we have to take water as well. Okay, water. So when you do the hydrolysis with water, this will convert into CH2OH. So this is the final product of the reaction. So from these options, correct answer is option C, because this is indicating the CH2 group. So these are the important questions from the chapter. So hope these are clear. So prepare well, all the best.